Hello, my name is Rogelio Martinez, and today I will be presenting to you a mini lesson on ionic compound synthesis. This lesson is normally taught for ESL students, meaning that 80 to 90% of the lesson will be done in Spanish. But for the purpose of my 50-hour service, I am doing the lesson in English. So today we'll be dealing with ionic compound synthesis. The objective is that students will be able to synthesize ionic compounds from metal cations and anions. Students will be able to write ionic formulas following nomenclature rules. And students will be able to use Lewis dot structures to determine the ionic structure of the compound. As a review, I've set here a periodic table of elements. We're going to be working with group 1 metals, which have a positive charge of 1, and group 2 metals that have a positive charge of 2. The charge is associated with the number of valence electrons that the elements share or donate to the nonmetals. The nonmetals that we will be working with are group 14, 15, and 16. Group 14 can accept 4 electrons. Group 15 will accept 3. Group 16, 2. And group 17, only 1. And I will explain to you what that means in the next slide. This is an example of how you would see it in my class. It is written in Spanish. It says write formulas. I will translate it for you. It says write formulas for the following ionic compounds. All right, it says complete the table synthesizing ionic compounds for each of the anion and cation pairs. Secondly, write the cation first and determine the subscript for each ionic compound that you synthesize to provide a neutral compound. The example that we're going to start with is potassium chloride. This is potassium. It has a plus charge of 1. And this is chlorine. So these are anions. And these are cations. And we're going to synthesize compounds mixing the anions and the cations in a way that they provide a neutral structure. The example they start us with is potassium, the reaction of potassium metal with chloride ion. Now, potassium is a group 1 metal, so it has 1 electron, a valence electron. The Lewis dot structure for that will look something like this. Potassium has 1 valence electron. Chlorine, which is the anion, has 7 valence electrons. And the octet rule says that in order for this compound, this mixture to form an ionic compound, it must be neutral. So chlorine, because it's more electronegative, is going to take that electron away from potassium, right? That will give you a potassium plus with no electrons. And this will give you chlorine minus. And now, because of the octet rule, chlorine has 8 electrons, potassium has 1 electron. It has no electrons, right? So that gives you potassium chloride, a neutral compound. Now, let's move on. We're going to do it by columns, right? From potassium, we're going to react it with hydroxide. Okay, the rule says if you put the potassium first, you're going to mix it with this, with hydroxide. Now we need to determine what is the subscript. Okay, well, potassium will donate 1 electron to the hydroxyl. But where is the anion? Is it the hydroxyl or is it the hydrogen? So we look at this, we look at the bond of oxygen with hydrogen. This is a covalent bond, but because oxygen is more electronegative than hydrogen, it will form the cation. So this reaction would say that we have 1 valence electron on oxygen and 1 valence positive electron from potassium, so it mixes in a 1-to-1 ratio. Now, oops, eraser, thank you. Now it gets interesting, because now we're going to say what happens when you mix potassium with the carbonate. Well, the carbonate Lewis dot structure will look something like this. So basically it will be carbonate like this. And the anions are these two. That's why you have a -2. So to understand how the formation of this ionic compound is that 1 potassium goes here and 1 potassium goes here. Now you have a neutral. Now you have a neutral compound, right? Net charge of 0. So that means that here, your carbonate will look like that, right? So we'll take 2 potassiums with 1 carbonate to form a neutral compound. So what's going to happen here in the next example, where you have potassium, and you're going to react it with this group, this phosphate group. Well, the phosphate group has 3 places where you can put a cation, right? 3 anions to match up with a cation to provide you a neutral compound. So you would have 1 potassium here, 1 potassium here, and 1 potassium here. So that means that you'll have 3 PO4. Now that will give you a neutral compound. Do you see how that works, right? The positive charge indicates the number of valence electrons that you have. Here, it indicates the number of potassiums that you're going to need to synthesize a neutral compound. Let's do magnesium. Let's do this row here. Magnesium. That's what the rule says. Write the magnesium. This is a +2, right? Group 2 has 2 valence electrons, means that it's going to require 2 anions to neutralize, to provide a neutral compound. This is 2, chlorine is 1, right? So this is going to provide Cl two. You see, the chlorine provides 2. The chloride accepts each chloride accepts 1 electron from the magnesium. Since magnesium has 2 valence electrons, you will need 2 chlorines. Let's go to the next example of the hydroxide. The hydroxide is going to be very similar. The rule says write the cation first. We're going to draw the hydroxide. Recall that the hydroxide looks something like this. It accepts one positive charge. So it'll take one of the electrons on magnesium. The magnesium has 2 valence electrons. Hydroxide has 1. Therefore, you will need two hydroxyl groups for each magnesium to provide a neutral ionic compound. Let's take a look at what happens with the carbonate. The rule says magnesium first, okay? Then you're going to have the carbonate. But notice that the carbonate has a -2. And the magnesium has a +2. That means that they will mix is in a 1-to-1 ratio to provide a neutral compound. The subscripts of 1 are never included in the formula. That's a convention. Let's see what happens with the next example that gets more interesting because it sort of explores another space. All right, the magnesium, start the convention first, magnesium. But notice how in this example, the phosphate has a +3, a -3. It's going to accept 3 electrons from the metal. The metal that we have is magnesium, which is a group 2 metal that provides 2 valence electrons to the reaction. We cannot mix these two in a 1-to-1 ratio. But there's a way of solving this problem. What you do is you make a table that looks something like this. You say the magnesium, right? Magnesium. Then you say, how many valence electrons will magnesium provide? 2. Then you take the phosphate and you ask how many valence electrons will this complex provide? How many anion centers will this complex provide? It's 3 because it's indicated here by the with the exponent of -3. To arrive at the ionic formula, you just do a crisscross.
Officer Smith, please report to the office. Officer Smith, please report to the main office.
So it's going to take 3 magnesiums, right? Let's write the phosphate here. And 2 phosphates. To give you this neutral ionic formula. Observe that every time that you come across a situation where you will not form a ionic compound in a 1-to-1 ratio, one must use this method to arrive at the correct molecular formula. All right, let's try the iron. Iron is a little bit interesting. We're going to leave the ammonia because the ammonia we're going to do it as classwork individual to see how well you grasp the concept. And then I'm going to come around to each one of the stations and see how you're doing with that exercise. But let's work on the iron for a change, okay? Iron is very interesting in that iron can exist as iron 2 or iron 3. This is the convention to express the cation, the iron cation forms. These are the predominant ones, and this is how you were going to see it in textbooks, in exams, and other things like that. Just so you're not going to see it like we have it here, it's a +3. Well, let's see what happens when you combine. And iron has a +3, has +3, and chlorine has only a -1. The rule says first write the iron, the question is how many chlorines will it require to form a neutral compound? Because you have 1 here and you need 3, then the subscript here has to be 3, right? Because you need 3 chlorines to form a neutral complex. I'm going to skip the hydroxyl, and I'm going to let you try that on your own. And then as I walk through, I'm going to answer questions or see how I can help or help you explain, or maybe you can explain to me how you arrived to your at your ionic formula, so that I can see how we're doing in the grasping and being able to synthesize new ideas, okay? So the one that we're going to do next is the carbonate. What is going to happen here with iron? Iron has a +3, has 3, is going to donate 3 electrons. The carbonate has 2, will accept 2. Notice how now we have the same situation again. Iron has 3, carbonate has 2, and now we can use this method to arrive at the correct ionic formula. It's always useful to write down this little table. So you write iron first, like this, and then you ask yourself, how many electrons will iron donate to the reaction? We see it's a +3, so we hear +3, right? We get the carbonate, and you ask how many electrons will the carbonate group accept, and we see that has a -2, so that's got a -2. Now all we have to do is crisscross. It's going to be iron 2. You see, iron 2. Carbonate 3. I've intentionally left some examples for you to try. The ammonium ones, this one, and this one. I'm going to walk. This is for you to do on your notebook. I'm going to walk around the classroom, and you can ask me if you need help, or I'm going to visit each station to see how you're doing to monitor your progress. Okay? So now it's a good time to ask any questions if you have them. If not, it's time for you to take out your notebook, maybe a pencil and an eraser, and you start working on your completing this table. And don't forget to put your name, the date, the class, and the period before you start doing any part of the work. This concludes my video for my 50-hour service that I will submit. Thank you very much.